All right, welcome to the first lecture of Unit 3 on atoms. Today we're going to talk about the structure of the atom, how to calculate the number of protons, neutrons, and electrons, and the mass. And then in our next class, we're going to be actually diving into the history of how we discovered all of this. So right now it's the technical details. Next class, it's the history. So first though, what are atoms? Well, these are the smallest particle of an element that still retains all of the element's properties, and it retains its identity in a chemical reaction. So it's essentially saying, take any element and get it down to the absolute smallest that it can go before it's no longer that element, before it loses all of its properties and its characteristics. So all matter is composed of atoms. All elements are composed of atoms. They're so small, though, that we have no way of visualizing them. Yes, we can see compounds and molecules now with very powerful scanning electron microscopes, and there was a first image of an atom very recently published in the past year or so. But we can't really visualize them on a scale that makes any sense to us. They're still these blurry images that don't really help us when we're studying them. So all of our knowledge is based on secondary experiments and theory. The basic structure of the atom has changed over time drastically as we have new information, as we hone our skills and bring new technologies into play. So at first, the theory was that atoms could never be divided. They were the absolute smallest particle, and they were the essential particle. Now we know that's not true. There's things called subatomic particles, but it was a fair place to start. And since we've discovered these subatomic particles, we've been able to discover more and more about the atom itself. So, what are these subatomic particles? First, if you break down that word, the prefix sub means below. So subatomic means below the level of the atom, something smaller than the atom. There's three of them. Protons, which are positively charged particles. Neutrons, which are particles that have no charge. They're not positive or negative. They're neutral. That kind of makes sense with their name. And then electrons. These are small negatively charged particles. So protons are positive, P for positive, neutrons are neutral, and electrons are negative. As you can see here, there's different abbreviations that we use for them. It's just a shorthand to make writing and doing problems a little simpler and faster. So protons are abbreviated P with a positive sign afterward. Neutrons are N with a 0, and electrons are E with a minus sign. Those are going to be definitely useful in the future when we're working more with these. Now, the structure of the atom, as I said, has changed over time, so we're going to talk about it on multiple different levels, especially as we get into the history. But the basic is the protons and the neutrons are found in the nucleus, the tiny central core of the atom. And the electrons orbit or travel all around the nucleus. So in our picture here, this dense blob in the middle is our nucleus. And all of our electrons, our negatively charged particles, are moving in paths around the nucleus itself. Now, just to give you an idea of scale of what we're talking about here, if we blew the atom up to a larger size, let's say the whole atom became the size of a racetrack, the nucleus would be the same size as a pea, a single pea placed in the middle of that racetrack. So the electrons, even though they're very, very small particles, take up most of the space of the atom to move around in. And the nucleus is so densely packed, these protons and neutrons are held so closely together that they would only take up the size of a pea. Now, most of the atom is actually empty space because, as I said, the electrons are very, very small. So even though they're moving in all that space, they don't make up most of that space. The man who first realized this said, even though I'm a scientist and I have logic, I'm still afraid sometimes in the morning to put my feet on the floor, knowing that most of what I'm stepping on is empty space. It's just kind of weird to think about that these things that make up everything are so empty and small. Now, these electrons, that as they're traveling around, they orbit, we say, and we'll find out later that they orbit in these paths called orbitals. But for now, what I want you to focus on is the fact that they move in different places based on the amount of energy they have. They have their own fixed energy level. Each electron has its own energy level, and only a certain number of electrons can fit in each energy level. We're going to get into that a little bit more in our next unit, where we really dissect electrons and how they affect chemical reactions. Now, the number of protons in an atom is always equal to the number of electrons. We want our atoms to be neutrally charged overall. We don't want them to be positive or negative. We don't want our matter to have an inherent charge to it. So in order to do that, we have to balance our positives and our negatives. Now, the neutrons are neutral, so the amount of neutrons doesn't really affect the charge of the atom at all, but it affects other things that we'll talk about later. So the number of protons always equals the number of electrons. Now, hydrogen is the simplest atom in the universe. It also happens to be the most plentiful atom in the universe. The next is helium, and the third is oxygen. Now, hydrogen is composed of only one proton and one orbiting electron. It has no neutron at all. But what makes hydrogen hydrogen? Why is that particular mix called hydrogen? How do we get other atoms and other elements? That is specifically tied to the number of protons. An element is defined by its number of protons. If you have one proton, you're hydrogen. If you have two protons, you're helium. So the definition of an element is literally how many protons it has. We call this number the atomic number. So the atomic number of helium, since it has two protons, is 2. The atomic number of oxygen, because it has 8 protons, is going to be 8. So if an atom has 6 protons, how many electrons must it have and why? I want you to write that down. Then the second question, an element has an atomic number of 3. How many protons must it have and how many electrons must it have? And finally, if an atom has 12 neutrons, can we know how many protons and electrons it has? Why or why not? So in answer to the first problem here, if an atom has 6 protons, how many electrons does it have? Well, remember that our number of protons has to equal our number of electrons. So in this case, this element has 6 electrons. Why? Because we want our atom to be overall chemically or electrically neutral, so we don't want any positives or negatives. So in order to balance the number of positive charges and the number of negative charges, we have to have an equal amount of protons and electrons. So now if an element has an atomic number of 3, remember the atomic number was the same thing as the number of protons. This equals the number of protons. So how many protons must it have? Well, it must have 3 protons. And then how many electrons does it have? Well, go back to the problem we just did. The number of protons must equal the number of electrons. So we must have 3 electrons to balance out that charge. Now in this problem, all we know is that it has 12 neutrons. So we haven't really talked about how the neutrons play into determining the number of protons and electrons. That's what we're getting into next. So how much does an atom weigh, and how do neutrons play into all of this? So although all three subatomic particles have mass, the electrons are so small that we often don't consider them when calculating the mass. If you added all of them up and you use scientific notation to do the problem, it really wouldn't change all that much. It's kind of like on your last test when I had you adding and subtracting the two numbers in scientific notation. You should have gotten the same answer for both of them. We were adding and subtracting a number so small that it essentially did not change the number at all, especially with rounding. So this means that if we want to know the mass of the atom, all we have to do is find out the mass of all the protons and the mass of all the neutrons. And we can add them together to get something that we call the mass number. So the mass number is the number of protons plus the number of neutrons. You do have to memorize this equation. It will become very second nature to you very quickly, but for now, maybe write it down, put it on a note card, memorize it somehow. The mass number is the number of protons plus the number of neutrons, and we consider that its mass. Now, oxygen, as an example, has 8 protons and 8 neutrons. Plugging that into our equation here, that gives us with a mass number of 16. So this is really simple math compared to what we were doing last unit. If you have any questions about it though, please let me know because I want to make sure you get this before we move on. Okay, so let's go back to some of these problems and get some immediate practice with this. If the element silicon has 14 protons and 14 neutrons, what is its mass number? And the second question is, if sodium has a mass number of 23 and an atomic number of 11, how many neutrons does it have? I want you to pause and try to figure out these answers for yourself. I am going to go over them with you, but try to use that as your double check. Try to figure this out on your own first. Okay. So silicon has 14 protons and 14 neutrons. What is its mass number? So remember, the mass number is just the number of your protons plus the number of your neutrons. So in this case, we're going to have 14 plus 14, which will give us a mass number of 28. So now let's do it in a little more complicated way. We know the mass number and we know the atomic number. Well, the atomic number, remember, is just the number of protons. So in this case, we know that the number of protons is equal to 11. And if we plug it into this equation, we can solve for our missing n number of neutrons. So 23 is our mass number, and it is equal to the number of protons, 11, plus the number of neutrons. When we do that math, you take 23 and you subtract 11 from both sides, and you get that the neutrons, there will be 12 of them. All right, let's move on. Now, how do the neutrons really fit into all of this? Why do we not just say then that, okay, well, there's always a set number of neutrons and it's always whatever the mass number minus the protons are? Well, that's because the number of neutrons in an atom can differ. I can have an element of carbon with a certain number of neutrons, but then I can go dig somewhere else and find an element of carbon with a completely different number of neutrons. These are called isotopes. They're atoms with the same number of protons, but different numbers of neutrons. So this means they'll all have different mass numbers. Now, because the neutrons are neutral, no matter how many you have, you're only affecting the mass. You're never going to affect the overall charge. So it still makes your element stay neutral. So an example is on the right here. Hydrogen has a couple different forms. Its natural form, where we have only one proton and one electron, so that's hydrogen 1. We have hydrogen 2, or what we call deuterium, where it adds a neutron to it. And these numbers are just referring to the mass number. Hydrogen 1 because I only have one proton, so my mass number would be 1 plus 0 neutrons, which is 1. In this case, I have one proton plus one neutron, so my mass number would be 2. And then you have hydrogen 3, or tritium, and that has 2 neutrons in it. So these are all what we would say isotopes of hydrogen. So since the protons and the electrons are the only charged particles, they are the only ones that are going to be involved in our chemical changes. The neutron doesn't change the element at all. Only the number of protons can change what element you're talking about. So carbon will always be carbon, even if it's in the form of carbon-12 or carbon-13 or carbon-14. It just has a different number of neutrons in each of its forms. Now, we talked about the mass number, but what about the mass when we have a bunch of different isotopes? I can take a sample and have different isotopes within the same sample. So how do I take the mass of that if they're all going to have different mass numbers? Well, this is where we use something called the atomic mass. It is the average of all the mass numbers of all the isotopes of an element that we find in nature. So this atomic mass is the number that's put on the periodic table. That's why you'll often see that they have very funky decimals following the number. So like oxygen is 15.999. That's because we're averaging all the isotopes that are found in nature. So we've said that there's all this information that's given about these elements. And where do we find that? Well, we find it on the periodic table. Each element is put in its own special square or box, and we put very specific information in there. We put the element's name. Obviously, we want to know what element we're talking about. But because these names are often long and we often have people working across the country and the world in different languages and different cultures, we shorten them to symbols. It makes it a lot easier to work with them rather than writing out these big long names. So the element symbol is always on the periodic table as well. Sometimes you will only have the symbol and not the element name. That's why I'm having you guys memorize a few of the common ones so you can learn their symbols quickly. You'll have the atomic number on there, and from this we can find out the number of protons and the number of electrons. And then at the bottom, or sometimes in the top right corner, you'll have the atomic mass. So this is the one where we average all of the isotopes. So from that, you can find your number of neutrons as well. Usually what you do is you just round to the nearest whole number. So in this case for carbon, it's 12.01. So that would round to 12 is the nearest whole number. Then I know that I have 6 protons, so I can find out that I have 6 neutrons in carbon-12. All right, so let's get some practice using this information that we find on the periodic table. So let's talk about the first one here, helium. So we're focusing on this guy now. What is the element name? Well, I just said that, but we can also find it right here. The element name is helium. What is its symbol? Well, it's He. That one kind of makes sense. Usually it's the first letter or the first couple letters, but don't always follow that rule because things can get kind of crazy as you go further down the periodic table where they're using Latin names or something like that. So now, what is the atomic number for this one? The atomic number can usually be found at the top, usually the top left corner or the top middle. So the atomic number for helium is 2. Now, what's the atomic mass for helium? That one's usually going to be found at the bottom, right here. Sometimes it may be found up in the corner, but the bottom is the most common. So the atomic mass for helium is 4.00260. Remember, this one is the average of all the mass numbers of the isotopes. So let's do a little inferring here, some math problems to figure out the rest. What's the number of protons in helium? Well, if we remember, the number of protons is equal to the atomic number. So in this case, we're going to have 2 protons. Now we know that the number of protons always equals the number of electrons, so that our atom is neutral. So in this case, that means I also have 2 electrons. But what about my neutrons here? Well, my atomic mass is essentially 4. If we round that number, it's going to be 4. So if I take my atomic mass, and I take my number of protons, I can find out my number of neutrons, which in this case is also 2. So we have 2 protons, 2 neutrons, and 2 electrons. So now our mass number, adding those up, 2 and 2, is just 4. Take a minute, pause the video. I want you to try to do this on your own for lead, and then come back and restart the video, and we will go over all of the answers to see if you were right. Okay, so erasing all of this now. Let's get all this stuff off so we can get our proper answers for lead. Okay, now what is the element name for this element down here at the bottom? Well, right here we can find it. It is lead. So as I said, you can't always go by the first letter or two. Sometimes we use a different symbol based on the Latin name or some other information about it. So in this case, our symbol is Pb. Our atomic number is going to be this number at the top, which is 82. So we can jump around here and say, now I already automatically know I have 82 protons and 82 neutrons, because my number of protons is the atomic number, and my number of protons always has to equal my number of electrons. My atomic mass is remembered down here at the bottom, which is 207.2. So if we round that to about 207, we can use our handy dandy little equation and find out how many neutrons we have. So in this case, our number of neutrons is going to be 207 minus 82, which gives us 125. So you can see here, we can't always just assume that the number of neutrons is always going to be equal to the rest of them. As we get further down the periodic table, the number of neutrons tends to increase significantly. So the mass number is just the 125 for the neutrons plus the 82 for the protons, which we used here, which is just 207. All right, if you're having problems with this, email me and let me know, and I will do my best to go over it with you. Okay. Pause the video, try to fill out the table on your own, and then double check yourself. I'm going to go through this pretty quickly when I do go through it after that. So if you have questions, write them down, make a note, and ask me in class. The atomic number is always equal to the number of protons. So I know that it's going to be 8 for oxygen, but we also know my number of protons is always equal to my number of electrons. So I also have 8 electrons. My mass number is just the sum of my number of protons plus my number of neutrons. I do that math, I get 8 neutrons. Now in this case, once again, we have our atomic number, so I know my number of protons and my number of neutrons. I don't know the mass number here, so that means all I have to do is just add together my protons and my neutrons, which is 11. Now in this case, I don't know my atomic number either, but I know my number of protons. So because of that, I know my number of electrons and I know my atomic number. So 35 is our mass number, which is just equal to the number of protons plus the number of neutrons. Do that in math. You get 18 neutrons. And now our last one, we don't have any of this first information. We're only working from a number of neutrons and electrons, but we know there are 12 protons because it has to equal my number of neutrons, or of electrons, I'm sorry. And I know that that makes my atomic number 12. Add up my number of protons and neutrons, and I get a mass number of 24. Last thing is standard atomic notation. So sometimes when you do not have the periodic table in front of you and you are working with these kind of numbers, you can just write things in what we call standard atomic notation, or just atomic notation. It is the symbol of the element with the mass number in the top left and the atomic number in the bottom left. So that's a little bit different than what we're used to. We're used to seeing that atomic number up in the top left, so don't make mistakes with that one. You'll have to really memorize that. So this is independent of what we'll see usually on the periodic table. This is normally for when we're working with elements on their own on a piece of paper. So another example is fluorine here, atomic number 9, mass number 19. Same with helium up at the top. And we always use the symbol, not the element name. All right, so that was it for this video. If you guys have any questions, please write them down. Otherwise, go ahead and get started on that atomic structure worksheet. Try to fill out the fill in the blanks as best you can. I know it might be a little confusing without a word bank, but if you think through it, you can usually find a word that fits in there really well. I am going to be a little lenient as long as it makes sense and it is the correct-ish answer. Whether you say, you know, positive or plus or something like that, I'm not going to take off points for that. All right, I hope you guys enjoyed this, and I will see you in class where we will discuss the history of how we discovered all this information. Have a good day.